4, conditional probability. So if it's conditional, then it depends. Conditional probability is the probability of an event occurring given that another event has already occurred. Conditional probability involves the use of the word and. Conditional probability probably involves dependent events. So if it's conditional, it depends on something. Dependent events are events whose outcomes are affected by each other. For example, if 2 cards are drawn from a deck without replacement, the outcomes of the second card depends on the outcome of the first card. So conditional probability or dependent events involve the same event. For example, draw a card, do not put it back, and then draw another card. So you've got to be doing the same thing. You can't be drawing a card and then flip a coin, right? If you do that, no matter what happens on the card, that will not affect what happens when you flip a coin. The other thing is you're going to see the words without replacement or without putting it back or something along those lines, something that implies that we are not going back to where we started. We actually, at the point where we're working out the second probability, we're actually working out based on something that's already happened. Okay, so that's what makes it dependent. Something has happened. We're working on another probability, and it depends on what happened the first time around. Okay, so the probability, this notation, the probability of B given A, that's how that's read. Probability that event B will occur given that event A has already occurred. And on your formula sheet, it looks like this. The probability of A and B. Okay, so make sure this involves and, which involves intersection. A intersect B is the probability of A times the probability of B given A. So it means the probability that B happens given that A has happened. And then this can be, of course, rearranged to look like this. So this is what's on the formula sheet. Probability of A and B, or you can read this, the probability of A intersect B, is the probability of A times the probability of B given that A has happened. All right, so what's that all mean? Let's run through this investigation. You have a red die and a blue die are tossed, which means you can tell them apart, right? You can tell what numbers on the red die, what numbers on the blue die. The outcomes are shown in the table. Consider the following 2 events. Event A is the sum of the 2 dice is 10. All right, you know what? Let's just go over here. We'll put little A. So this is event A. The sum of the 2 dice is 10. Event B is the number on each die is the same. So this is event B. We've got 2 1s, 2 2s. In other words, double. The number on each die is the same. So state the following probabilities. Now with dice, we know there are 6 outcomes for the blue. Right? You just take fundamental counting principle, right? You got the blue die, blue, you got red. There are 6 outcomes for blue, 6 for red. There's 36 total outcomes. The probability of event A is 3 out of 36. Now, I'm just going to leave it as its raw probability. Okay, so by raw probability, just the actual count. Right? There are 3 ways of getting a 10. You can get a 4 on the blue and 6 on the red. You can get a 5 on the blue, 5 on the red. You can get 6 on the blue, a 4 on the red. That's 3 out of 36. Probability of event B, the numbers being the same, is 6 out of 36. 6 out of 36. The probability of B given A. So the probability that the numbers are the same given that the sum is 10. Right? That's this guy here. So we need a sum of 10. That's first. First we need a sum of 10. Then we look to see if the numbers are the same. And we can see that's 1 out of 36. Okay, one of the outcomes. So the probability that given that A has happened, probability that we have doubles is, wait a minute, it's not 1 out of 36. That's 1 out of 3. Okay, so given that A has happened, we have 3 outcomes, right? There's 3 ways of getting a 10. One of those involves doubles. Okay, the probability of A given B, given that we have doubles, okay, which is 1, 2, 3, 4, 5, 6, the number of ways, so given that the number is the same, the probability that we have a 10 is 1 out of 6. Right? So there are 6 outcomes where we have doubles. One of those 6 outcomes is that we have a sum of 10. The probability of A intersect B, the intersection of A and B. So the probability of A and B. So the probability that we have a sum of 10 and doubles is 1 out of the 36. That's 1 out of 36. And the probability of B and A, so the probability of doubles and that we have a sum of 10 is also 1 out of 36. Verify the following. So the probability of A and B is the probability of A. The probability of A is 3 out of 36. 3 out of 36. These actually can be reduced because we're multiplying, but 3 out of 36 times the probability of B given A, which is 1/3, and we end up with 1 out of 36. Probability of A or B is A and B is 1 out of 36. Do this one. The probability of B, the probability of event B is 6 out of 36. Okay, 6 out of 36. The probability of A given B, so the probability that A happens, probability that we have a sum of 10 given that we have doubles, is just this 1 out of 6. Okay, 6 is canceled. Ends up as 1 out of 36. Also 1 out of 36. That's this guy here. Okay, so that verifies the formula, okay, using a nice little table here, the chart. So a table, this is a way of listing the sample space. Right? These are all the possible sums. There are 36 ways of getting those sums, anywhere from 2 to 12. The number of ways that you can get a 10 is 3 ways, right? So the probability given A, so there's 3 outcomes there. One of those is that you got doubles given that you have a sum of 10. Okay, so remember, given that's already happened. Okay, let's work out some more, do some more examples. Sammy draws 2 cards from a deck of 52 cards without replacing the first card. So it's very important, especially when you're doing the same event, right? As we'll see in the next lesson, because in the next lesson we will be replacing, okay? And again, what that'll mean is, well, we'll get to that in tomorrow's lesson. What happens if we put it back? Calculate the probability that Sammy draws both hearts. So again, this is an and probability. So the probability of heart and heart is the probability of getting a heart times the probability of getting a heart given that we've got a heart. So let's just think about what that means. So the probability of getting a heart is 13 out of 52. Whatever our first event is, that's basically your normal probability that you would come up with just right off the bat, right? Is that there are 13 hearts out of 52 cards. Now, this is dependent. So what's the probability the second card is a heart, given that you got a heart? So if you've got a heart, one of those hearts is gone. There are 12 hearts remaining. And if you got a heart on the first card, without replacing it, there are 12 parts remaining out of the 51 remaining parts. So 13 out of 52. This is basically normal probability we would always just work out anyways. But on a dependent probability, the number in the numerator is always going to go down by 1 because there is one fewer card, right? We did not replace it. And this is equal to, okay, and we can just go into our calculator, which maybe we can turn on. Yeah, let's clear that. Now if I got fancy, I can get fancy. Alpha, F1, sorry, alpha F, numerator over denominator, right? Go 13 over 52, right? Kick out of that, times alpha F1 again, numerator over denominator, 12 out of 51. And the fact that I've entered these as fractions means my answer will be a fraction. 1 out of 17. The probability is 1 out of 17, which means if I drew this, not 17 times, that's too much. If I drew this 170 times, then 10 times I would expect, right? 170, 10 out of 170, 100 out of 1700. What that means, any probability is over the long run, right? And remember, expected value, right? So 1,000 times, probability is 1/17, and there's 1,000 of these, right? We do that 1,000 times, then our expected value, multiply this, be 1,000 out of 17,000 would be an equivalent thing, fraction. Okay, let's say you've just got a normal calculator, just go bracket 13. I like to bracket these things. 13 out of 52 times 12 divided by 51. Okay, that'll give a decimal, of course. Then you go math, enter, enter. Because most of the time, we're going to want to express this as a reduced fraction. Okay, next one. So dependent probability, given that something has happened. According to a survey done in January, 85% of Canadians own a computer. Of those, 40% own a laptop. Determine to the nearest tenth of a percent the probability that any Canadian you met in January would have a laptop. So, probability of laptop given computer. So the probability you have a laptop given that you have a computer. So I'm just going to write the formula. It's off the formula sheet. Probability of A union B, A intersect B is the probability of A times the probability of B given A. Now, we want this, we want to work out probability of B given A. Probability of B given A is probability of A intersect B over the probability of A. And in this case, B is laptop and A is computer. So where we see B, we're going to put laptop. Where we see A, so the probability of computer, that's your A, and laptop over the probability of computer is equal to. So the probability that you have a computer which is a laptop is 40%. And the probability you have a computer is 85%. So that's 40 over 85. Now, see here it says nearest tenth of a percent. Now these are both percents, but when we divide them, so 40 divided by 85, we're just going to get a decimal. To convert that to a percent, we multiply by 100. And to the nearest tenth, rounding, so 47.1%. Okay, 47.1%. So the probability that you have a laptop, given that you have a computer, you have to have the computer first, right? You have to have that computer, is the probability of computer and laptop, okay, which is the 40%, right? over the probability of computer, which is the 85%, and that works out to 47.1%. Next up, making predictions using tree diagrams. There are 2 blue and 3 red marbles. Okay, 2 blue. You get to see this in color. 2 blue and 3 red marbles in a bag. So we have 5 marbles in this bag. So, question, what's the probability that, and you're going to draw 2 marbles, one after the other without replacement. Okay? Dependent events. Dependent events. Okay? Which means probability of A and B is the probability of A times the probability of B given A. That's the dependent events. On your formula sheet, you're going to have 2 formulas for the probability of A and B. And one of them is for dependent events, which is this one, right? Given A. So given that something has happened. So, it depends on this. That's your dependent event. And then in the next lesson, we'll do the one where the other formula, which is, wait for it, independent events. Okay, probability of the first marble being drawn is a blue marble. Probability of getting blue. There are 2 blue out of 5 marbles. Probability of the first marble being drawn being a red marble. Okay, again, first marble, so it wasn't blue. Probability of draw is 3 out of 5. Now note, these add up to 5 out of 5 or 1. Because that's every possibility, right? Either it's red or it's blue. There are no red-blue marbles. If a red marble was drawn first, okay, so let's look at what we have. If a red marble was drawn first, we still have 2 blues. But now we only have 2 reds, right? A marble is drawn, it's not replaced, so there's 4 marbles left. So if a red marble was drawn first, that's what's in the bag. The probability of the second marble drawn being blue, we have 2 blues out of 4 marbles. So 2 out of 4 or 1/2. Now, being as we're going to be doing multiplying, it's okay to actually reduce these, right? When we're doing the OR probabilities where we are adding, then we don't want to reduce. Okay, so starting with this bag, the probability of being blue is 2 out of 4. If it's starting with that bag again, if it's red, that's also 2 out of 4 or 1/2. All right, what if a blue marble was drawn first? Okay, then we have 1 blue marble left. Right? Remember, we're not replacing, and we have 3 red marbles. So this is the bag we're starting with for the second draw. So here, let's just separate these out. Either this is what's going to happen, right, if a red is drawn first, or this is what's going to happen. You'll have a blue drawn first. Go through. Okay, so one of those 2 possibilities. So if blue was drawn first, the probability of getting blue is 1 out of 4. There's 1 blue marble left out of 4. And if blue marble was drawn first, probability of getting red, there are 3 reds out of 4. Okay, now again, these have to add to 1, just as these have to add to 1. So these guys add to 1, these guys add to 1, these guys add to 1. Whatever your probabilities, if you're taking into account everything that could happen, then it has to add to 1. So we make a tree diagram, right? We say we start with 2 blues and 3 reds. So here's our starting point. It's 2 blues, 3 reds. And we're just going to go right back up to here and say if the first marble drawn is blue, so if the first marble drawn is blue, the probability of drawing that is 2 out of 5. And the other choice is that the first marble drawn is red, which is 3 out of 5. If the first marble drawn is blue, we have 3 reds left and 1 blue. Then, if we draw a blue, so if blue is the first marble drawn, the probability of the second marble being drawn, I mean, we can look up here, we can just look here. Say that probability is going to be 1 out of 4. Okay? And what we will be left with is a bag containing 3 red marbles. If the first marble drawn was red, then we have 2 reds left and 2 blues left. Oops, wait. If we do red, if the second marble is red, that's 3 out of 4. Okay, so we need to fill in each branch. This is just your basic tree diagram, right? But it's a tree diagram based on conditional probabilities. So the probability of getting a blue as the second, there are 2 out of 4, right? Or 1/2. And probability of drawing a red as the second marble is 2 out of 4, or 1/2. So if we want to work out our probabilities, the probability of getting a blue and then another blue, right? And right here, let's just fill this in. If we got a red here, then from this we would have one. We got a red. We would have 1 blue and 2 reds. This is what would be left at the end. We're going to be left with a bag of 3 marbles. If we drew a blue here, we would have 1 of these, and 2 reds. Again, which we would end up with. And I mean, this ending one doesn't really matter in a sense. And if we did that, we would have 2 blues and 1 red. So we can look at it as this is what would be left. So the probability of blue and blue, is going to be 2/5. Well, here, let's do this. Let's throw the formula in. It's the probability of getting a blue on the first marble times the probability of getting a blue on the second marble. So this is the second, given that the first marble is blue. So the tree diagram can help us out because we've listed all the probabilities. We could also just do these by the counting. So the probability of blue on the first marble is 2 out of 5. Times 1 out of 4, which is 2 out of 20, or 1 out of 10. So the probability of getting a blue and then a blue. Probability of getting a blue followed by a red is the probability of getting a blue times the probability of getting a red, given that we got a blue on the first one. So the probability of blue is still this first probability, 2/5, first marble drawn. Probability of getting a red, given that you've got a blue, right, 3 out of 4, is 6 out of 20, which is 3 out of 10. Probability that your first marble, so you get a red and then a blue, would be the probability of a red times the probability that you got a blue. Actually, the probability times the probability that you got a blue, given that you got a red. So the probability of a red, our first probability, is 3 out of 5. Probability that you got a blue, given that you got red, is 2 out of 4. It's 2 out of 4, which is 6 out of 20, or 3 out of 10. Probability that you got a red and then a red, so probability of red and red is equal to the probability of getting a red with the first marble times probability the second marble is red, given the first is red. So probability of a red, our first probability, 3 out of 5. There are now 2 reds left, 2 out of 4, is 6 out of 20, which is 3 out of 10. So we have 4 branches. They are the probability that you've got 2 blues, right? You got a blue on the first draw, and then without putting it back, you got another blue. Probability you get a blue on the first draw, and then without putting it back, got a red on the second. Probability you get a red on the first, and then a blue. Probability you got a red, and then a red. Now that's all that can happen, right? You can either get a blue and a blue, a blue and a red and a blue, or a red and a red. Which means if we add up all of these probabilities, 1/10 plus 3/10 plus 3/10 plus 3/10, well, that's 3, 6, 9 is 10 out of 10. So that's equal to 1. So the probabilities at the end here, this is all the things that can happen. They have to add up to 1, as do these individual probabilities on each branch. So each branch says this is what can happen. You can get a blue or you can get a red. And those probabilities, 2 out of 5, 3 out of 5, they add up to 1. You can get, second draw, a blue and then a red. Those probabilities add up to 1. Second draw, you can get a blue or a red. Those probabilities add up. Remember, it's or, right? You get blue or red. 2/5 plus 3/5 is 1. Second draw, blue or red. 1/4 plus 3/4 is 1. Second draw in this case, blue or red. 1/2 plus 1/2 is 1. In these cases here, okay, there's 4 possibilities. You get a blue, then a blue. You get a blue, then a red. You get a red, then a blue. You get a red, then a red. All of those have to add up to 1. All right, let's move on. Last example. Each day, Ms. Teacher gives the class a warm-up question. It is a numeric response question 40% of the time and a multiple choice question 60% of the time. Bobby gets 80% of the multiple choice questions correct and 70% of the numeric response questions correct. Bobby answers today's question correctly. What is the probability that it was multiple choice? So we want, what is the probability it's multiple choice given that it's correct? Okay, so we can use the tree diagram to help us figure this out. So it's a numeric response. So the question is either numeric response or multiple choice. It's a numeric response 40% of the time. Let's call that 0.4. Which means multiple choice. Now, they didn't even really have to tell us this, right? If we knew it was only the 2, these probabilities have to add to 1. So that's 0.6. These 2 branches add to 1. Okay, numeric response, then you can get it correct or not correct. Now, when we put a bar over top of something, it means the complement. It means not. Okay, well, actually, that's a prime. I'm going to use, let's just do this. Correct, not correct. Correct, not correct. So, what do we get? If it's multiple choice, he gets 80% of the multiple choice correct. If it's multiple choice, given that it's multiple choice, he's got 0.8, which means he gets 20% of those wrong. Again, these have to add to 1. So given that it's multiple choice, right, he gets 80% correct. And 70% of the numeric response. So if it's numeric response, this is 70%, this is, right, these have to add to 1, that's 30%. So if we follow each branch, right, what we get is, this is numeric response and correct. Okay, which will be 0.4 times 0.7, which is 0.28. You know what, let's put that over here. 0.28. Numeric response, and he gets it wrong. It's the probability of numeric response and not correct is 0.4 times 0.3. Which is 0.12. The probability that it's multiple choice and correct, probably multiple choice and correct, is 0.6 times 0.8, which is 0.48. And the probability that it is multiple choice and wrong or not correct is 0.6 times 0.2, which is 0.12. Okay, now let's just check things over. So do these add to 1? 0.4, 0.6. Do these add to 1? Yes, they do. Do these add to 1? Do these add to 1? All right, let's see. 0.28, this will make 0.3, 0.4, 0.88, 0.9, 1.0. So the big check here is that this adds up to 1.0. Now, what is the probability given that it was correct? So the ones that are correct are these. So the probability of him getting it correct is 0.28 plus 0.48, which is, goes math in head, 0.76. So the probability that he gets it correct is 0.76. So that's our denominator, right? We got 0.76. Now, what's the probability that it was multiple choice? That's this guy. So that's this. The probability that it's multiple choice. So given that he got it correct, that's the 0.76. Probability that it's multiple choice is, mess that up. Okay, so this probability that we're trying to figure out is, so first of all, he has to get it correct, right? So he's got 76%. He's got 0.76 that he's got it correct. Then the probability that it's given he's gotten it correct, that's our bottom. Probability of multiple choice is 0.48 out of 0.76. Cannot do in head. So 0.48 divided by 0.76 is 0.6315. So 0.63, let's just check, 16. So 63.16%. Okay, so the probability that it was a multiple choice question. So given that he got it correct, probability it was multiple choice is 63.16%. Okay, so really the easiest way to do this question, and you may not think this is the easiest way, but the easiest way to do this question is in fact to do the tree diagram, because at every step of the tree diagram, you're self-checking. Do these add to 1? Do these add to 1? Do these add to 1? These are just a straight multiply. Okay. You can split each one out. No, let's just not do that. So all you do is you just follow each branch, multiplying each branch out, right? Numeric response and correct, 0.4 times 0.7. Your next check is, do all of these guys add to 1? And then you're saying, okay, what's the probability of his multiple choice, right? So given that he got it correct, okay, that's these guys. Given that it's correct, I'm only interested in these two lines. These two lines are the ones where the question is correct. Okay, so the chance of getting it correct was 0.76, right? You're going to add these two together. And then the probability is multiple choice. Now we look at this one line. This is the multiple choice correct. So 0.48 out of 0.76. Okay, complicated, but you know, tree diagram makes it fairly easy to work out, right? And then you've got this same idea of the tree diagram here, each of which have their dependent events, and away we go. So we're done. Lesson 5, 4, 5.